So today we are moving on into Chapter 4. Sorry, let me just get myself situated here. All right, Chapter 4. It's all about correlation, or actually, I should say, relationships between two numeric variables. Okay? So that's what Chapter 4 is about, relationships between two numeric variables, and we will talk about correlation and linear regression. So we can think of any two numeric variables, and we can ask, are these two numeric variables related, or will they have nothing to do with each other? Okay. And so let's see. For example, one example is the age of a car in years Okay, so that's a numeric variable, right? Car can be 0 years old, it can be 10 years old, 7 years old, 23 years old, or 3 or 4 or 5, you know. Probably a lot of cars on the road today are around 5 years old or something around there, whatever, more or less. Okay, so that's one variable. Okay, the age of the car in years, and we can see if that's related. Is that related to the mileage on the odometer? Okay, so these are two numeric variables. And we want to know, is there a relationship between them? Okay, so just imagine going to, you know, a big parking lot, you know, and you got little cars parked here, okay? And you got lots and lots of cars all over the place. All right, these are awesome cars. Okay, it's the latest model. Tesla Model E will look just like that. And haha. There, just imagine going across, and you know you're looking at 1,000 cars or 600 cars or something like that. Okay, so we look at, you know, say 600 cars. Maybe not even that many. Okay, and for every single car, we record these two numeric variables. Okay. So think of our data table. What would our data table look like? How many rows and how many columns would I have in my data table?
2 columns. 1 average year card.
How many? I would have.
Isn't it 2 columns and 600 rows?
Okay, yeah, I would have. I might have an identifier column, maybe. It doesn't matter. Okay, so we'll have a ID, but then we'll have the age, and we'll have the mileage. So we'll have at least 2 columns, and we're going to have 1 row for every single car. All right. So maybe the ID, we use some plate, right? 7 ABC 1 2 3, and the age of the car is 1 year, 1.2 years, I don't know. And the mileage, it has 11,026 miles. Here, I'll just write 11026. And then maybe another car, it's got, you know, 5 DEF, 6, 7, 8, whatever. Okay, I'm just making up plate numbers. And this car is 3.1 years, and it has, I don't know, 30,653 miles. Okay. Does this make sense? And we just keep going, and we're recording all of this data for how many rows? 600 rows, right? 600 rows, one row for each car. Okay. All right, so let's say we're going to plot all of this data. Okay, we make a plot. And this is called a scatter plot. Apparently scatter plot is one word, although most programs don't recognize it. All right, so we're going to plot a scatter plot. And if you can recall from like algebra, you can plot coordinate pairs. Okay, so on one axis, we're going to do one of the variables. So I'm going to pick age. And then on the other axis, I'm going to put the mileage. Okay. So a dot right here, if I put a dot at the origin, what does this dot represent?
0 mileage on a brand new car.
Yeah. A dot at the origin represents a brand new car right out of the factory, 0 miles driven on it. It's also 0 years old. Okay, does that make sense? Okay, so this would be brand new car, 0 years old, 0 miles driven. And then we can put little tick marks for the different numbers. So we got 1, 2, 3, 4, 5, you know. So my chart only goes up to 6 years, but I know cars have many, can be much older than that. So, and this will be, we'll do 10,000, 20,000, 30,000, 40, I'm just gonna write 40K, 50K, okay? And then so we would plot every single one of these cars. So this first car, which is, you know, ID 7ABC123, is 1.2 years old and has 11,026 miles. So we would put a dot something right around there. Is that okay with you guys?
Yeah.
All right. And then the other one would be 3.1 and has 30,000 miles, 30,653, and so we would put another dot right there. Okay, so these two dots are from our table. Okay, so these so these are plotted on the table, these two. Or I'm sorry, plotted in the scatter plot. And then now I'm going to just pretend to draw a whole bunch of dots, okay? So what would a dot, I'm going to use a different color to show made up dots that I'm just making up on the fly, okay? So a car right here, a dot right there, what would that represent?
Age 3.
Yeah, a car that's 3 years old and probably has only 5,000 miles on it, okay? So that would be someone who bought a car and maybe has a very short commuting distance or just doesn't do a whole lot of driving, right? Okay, and then you know, somebody who makes a bunch of cross-country trips, maybe, you know, they have a dot all the way up there, okay? 2 years old and they've already put 60 grand, 60,000 miles on the car. So it's a lot of driving, right? like truckers. They put tons of mileage on their vehicles, but they're big trucks. Okay, and then we just so I'm just going to just draw a whole bunch of other dots, kind of indicating other cars that might be. And so as you're, I took a moment to just talk about these two extreme points here. So this would be, 3 year, I'm just going to point this out. 3 years old, 5,000 miles. And this is 2 years old, but 60,000 miles. Okay, and then we got a whole bunch of other dots that I'm just making up. But we could imagine it looks something like this. Yeah? Okay. And then so somebody asks, well, is there a relationship between the age of a car in years and the mileage on the odometer? And you would say, yes. Okay. And what would you say the general relationship is?
The older the car, the more miles.
Yeah. So in general, cars that are older will have more miles driven. Okay, and that's essentially what this entire chapter is about. We're going to look at different numeric variables, 2 numeric variables at a time, okay? And then we're going to ask, is there a relationship between these 2 numeric variables? Okay, and so this is a very, I think, a simple but understandable example. We're going to have other examples that maybe just seem a little bit weirder, or it's not so clear, okay? But we're going to talk about all of that. Is this okay, where we're heading today?
Yes.
Great. Let's see. This is... Gotta find the correct folder. Lecture slides. Okay, so today is April 14. And this is slide 1. Great. Okay, so notice, I guess one thing to point out is that in this data set, we were looking at a whole bunch of different cars, 600 different cars. Not the same car at different points in time, but a whole bunch of different cars just all at once because they were all parked in the parking lot. Okay, so I'm going to just draw kind of a few maybe scatter plots that kind of give us an idea of how we can describe different trends and relationships, etc. Okay. So the first one that we looked at. Okay. So the example with the cars and the mileage, the age of the car and the mileage, looks something kind of like this. If we had to classify it, we would classify it as this thing. Okay. And this is known as a positive trend. I'm going to label the axes just with the generic letters X and Y, okay? But what they really represent are 2 numeric variables. Okay, so in the other example, X was the age of the car, Y was the mileage driven. But in our case, for the generic form, we're going to say X and Y. So we'll say, in the last example, X was age of car, and Y was mileage driven. Okay, and the name of the idea behind a positive trend is that larger values of X, larger values of x are associated with larger values of y. And the opposite, small x is associated with small y. Okay, so that would be positive trend. So the age of cars and the mileage driven. Can you guys think of other numeric variable combinations that might have a positive trend?
Height and age.
Age and height for children, right? So for children, older kids tend to be taller than younger kids, okay? But once you reach adulthood, we don't have a positive trend anymore, okay? So we could say age and height for children. What else might have a positive trend or positive relationship? Height and weight. Okay. So maybe this trend will not be as strong, but yes, in general, height and weight will have positive trend. In general, people who are taller than average, generally weigh more than average. People who are shorter than average, in general, weigh less than average. Of course, there are exceptions, just like with the cars. You might have an old car with little mileage, or you might have a fairly new car with lots of mileage. There's always going to be exceptions, but overall, if you looked at the general population and we're looking for an overall trend, we would see this positive trend where large X is associated with large Y and small x is associated with small y. Okay, so that was positive trend. What do you think? Well, let me draw the dots first. Yeah. You guys have all figured out patterns well. Okay, so if this is called positive trend, this over here would be called a negative trend. Great. Negative trend, or you can just say negative direction. Again, we're just going to use the generic x and y. And so here, large X is associated with what?
Small y.
Yeah, associated with small y, and small x is associated with large y, exactly. All right, give you guys a second to copy that down. All right, so what two numeric variables will have negative trend?
The age of a car and the value of a car?
Age of a car and the value of a car. Very good. Age of car and value of a car. All right. In general, we'll just say for most cars, not classic Ferraris or things like that. Okay. We'll say in general, as cars get older, their value goes down. Okay. So large X, an old car, would be associated with small value. Okay. And small x, a new car, will be associated with large y, large value. Okay, so age of a car and value of a car. Very good. Any other examples of negative trends that you guys can think of? Yes? Age of a car and amount of repairs. I would actually argue that that would be a positive trend because older cars will probably need more repairs, younger cars will probably need, or newer cars will probably need fewer repairs. So that would be large X with large Y, small x with small y. Maybe altitude and air pressure. All right, I don't know if you guys are familiar, but altitude and air pressure. So as you climb a mountain or things like that, the air pressure goes down. and you know, things boil at a lower temperature, your ears pop, things like that. So altitude and air pressure. If you have high altitude, whatever x is, the air pressure generally is lower. At sea level or below sea level, the air pressure is higher. Things like that. Okay, and lastly, I guess a few things could fall into here. We can just have something like this. This will be no trend. No trend, neither positive nor negative. Hang on, I see your hand. Let me just finish writing this. Okay, and we had a question.
So can two numbers who have a relationship have no trend on a scatter plot, or is it?
I'm sorry, your question again is...
Two numbers who have a relationship, like the graph that we were doing previously?
So two numeric variables, okay.
Yeah.
They have a
They
relationship.
no trend if we graph it on a scatter plot?
So if they have no trend, then that would mean that there's no relationship. Okay? So no trend. Let me... also under no trend would be... This would also reflect no trend. This is supposed to be completely flat here. Okay, it's neither positive nor negative. So that would be no trend. Okay, neither positive nor negative. So that means, you know, large or small values of x are not associated with large or small values of y. Okay, so examples would be something like shoe size and IQ. Okay, so someone's intelligence is not associated with their shoe size, as far as we know. Okay, people with big feet can have high or low IQ. People with small feet can have high or low IQ. And the opposite is also true. Okay, people with high IQs can have big feet or small feet. Low IQs can also have big feet or small feet. So there's no real relationship there. So we say no trend. Okay, so these words positive, negative, or no trend, these are also known as the direction of the relationship. Okay. Okay, so positive, negative, or no relationship can all be known as the direction of a relationship or association. Okay, and the key again is we're always dealing with two numeric variables. Okay, we will never talk about scatter plots if we have a categorical variable or anything like that. All of this is for two numeric variables. All right. Is that okay? Go back? Sure. Whoops. Oh, crap. I cannot go back. Hang on. Making my life hard. April, see, and didn't. There we go. Okay. Okay, is that all right? let me just go up a folder. Okay, so I want to talk about the shape of a relationship. Okay, and in our class, we're only going to be dealing with linear shapes, okay, linear relationships. So we have linear, and anything that's not linear, we just call nonlinear. So maybe in a more advanced statistics class, we would define all of these other things. But linear basically means it looks kind of like a straight line, okay? So you've got dots, and it looks like we have a straight line, kind of, okay? Nonlinear, anything, I should have used a different color. You know, if your points go like that or they go like this, these would be nonlinear trends. See, if you have dots that don't seem to go in a straight line, then we have nonlinear. Okay, so our course will only deal with linear. Okay, if you see something nonlinear, you just say that's nonlinear. We can't analyze it. Okay, so we're going to learn what we call linear regression. So linear regression, which is what we're learning, is only appropriate for linear relationships. Okay. Actually, and let me just throw in also correlation and linear regression is only appropriate for linear relationships. Okay. So correlation, if you guys can read that. 2 R's, E-L-A-tion. Correlation and linear regression, now it's R, are only appropriate for linear relationships. Nonlinear relationships do exist, but we will not learn how to analyze them. Okay, so we're talking about the shape of a relationship. Now, sometimes there's lots of scatter in these points, and I'll draw some examples, but as long as it looks like a straight line can kind of summarize the data, then we will say it's a linear relationship. Okay, so as long as a straight line, so linear means,
So it could either be positive or negative.
yeah, so whether it's positive or negative, linear just means a straight line is a reasonable approximation. Could be positive or negative. I know I drew a positive here, but so linear just means straight line. If you get something that's not a straight line, linear regression or correlation, not appropriate. All right, I'm going to go to the next slide. Okay, and so we have the direction of a relationship. No, I'm sorry, we already did direction. Strength of a relationship. just like relationships between people. What is the direction this relationship is headed? Positive or negative? How strong is our relationship? We're going to talk about that now. Not ours, but okay. I guess linear shape of a relationship, maybe that doesn't quite work, but whatever. Okay. Strength of a relationship. So let's talk about that. Okay. So strength of a relationship, you can have strong and you can have weak. So strong means there is very little scatter. Very little scatter in the points. And another way to look at strong is that if you are given a value of x, you can make a good prediction of y. Good prediction for y. Okay, so here I'll do a negative example, but maybe you have points that look like this. Okay, so just not a whole lot of scatter in the points. Strength of a relationship, we've got a negative relationship that's strong. Okay, so this would be a strong negative relationship. And let's say you were given this value of x. Okay, well, given this, we can make a very good prediction, and we can say our prediction for y is going to be right here. Okay, so if we're given this x value, we can make a prediction for y and not have a whole lot of guesswork there, right? We can go right in this kind of zone and say y is going to be probably very close to here. Okay, so if we have a value for x, we predict y will be right around here. Does that make sense? Okay, because there's not a whole lot of scatter. You know, at most y is going to vary by just a few points. I know these are just generic things, but that's the idea for strength of relationship. Okay. On the other hand, if you have a weak relationship, so maybe I'll do another negative relationship, but weak, you have lots of scatter in the points. Okay, so weak relationship means lots of scatter in the points. Let me use the black pen. And if you are given a value for x, you can make a prediction for y but it will not be, it is not expected to be very accurate, or I should say not expected to be very precise. Okay, so here's a plot with x and y. And so let's say we are given a point, and we say x is right here. Okay? Alright, so if x is right here, where do we predict y to be? Okay, we can draw our dotted line, and we'll say, okay, well, I'm going to predict y is somewhere around here, but really, I'm going to draw little kind of error bars. Y could be anywhere within this zone, okay? This is probably our best guess, right in the middle, but we would not be surprised if y was up here or y was down here, okay? Whereas over here, the tolerance is much tighter. Okay, so this would be a weaker relationship, okay? And you got everything in between. All right, so you have strong and weak. I guess I could write a little bit more detail. So given a certain value for x, we can predict y but y could be quite different from our prediction. Is that good? Okay, so all of these things, well, not all of them, but so for linear relationships, we have a numeric summary. What's another word for numeric summary? Okay, so we said things that, numeric summaries summarize informations about data sets. So things like the mean and the median and the IQR and the range and the standard deviation. So another word for numeric summary is a statistic, right? So for linear relationships, we have a numeric summary or a statistic called correlation. Okay? So that's all it is, right? The mean is a statistic that tells you what?
Average.
The average, okay, and another word is for average, or the idea behind the mean or the median is that it tells you what? The middle or the center of our data, okay? The standard deviation is a statistic that tells us what? The variation or the spread in our data. Are the numbers similar to each other, or are they quite different from one another? Okay. Correlation is a numeric summary or a statistic. Okay. It tells us, correlation tells us about the direction and strength of a relation. Direction and strength of a linear relationship. Okay. So whereas before you would look at a scatter plot and we would just say it, has a positive direction and it looks like the points are scattered a lot or not a lot of scatter. Correlation gives us a number there. Okay, and like all of the other numeric summaries, its power is in that it makes it easy to compare one set of data to another set of data. Okay, so the symbol for correlation is r. Okay, it's a lowercase r. And r can be any value between 1 and -1. Okay? And the sign of r is the direction of the relationship. So after I finish talking about correlation in R, we'll take a break, okay? So maybe 10 more minutes here. So the sign of R, so if R is positive, the relationship has a positive direction. If R is negative, direction is negative, right? So if R is greater than 0, direction is positive. And if R is less than 0, direction is negative. Simple enough. Okay. And then if R is close to 0, the relationship is weak. If R is far from 0, so in other words, close to 1 or -1, then the relationship is strong. Okay, so digest all of this, okay? And R is just the result of a formula, okay? You will not be expected to calculate R, okay? R is the result of a formula. You are not responsible to calculate R. Okay, you are responsible to know the appropriate interpretation of R. Okay. R or correlation. So R does exist for nonlinear relationships. But it is not appropriate to use. Does that make sense? So, because it's just a result of a formula. So you plug the numbers into your formula or equation, you're going to get a value for R between -1 and 1. But if it's a nonlinear relationship, the interpretation of R is not appropriate. Okay? It's not appropriate to use R for nonlinear relationships. So let's just go through a couple examples of different values of R. Did you guys get this all written down? Okay, we'll wait. How about now? All right. I'm going to count to 5 in my head, and then I'm going to go to the next slide. All right, there we go. Sorry if I left you behind. Okay, so let's do some example plots. Okay, so the direction here is what?
Positive.
Positive, so R is going to be positive. And is it strong or weak or what?
Strong. Strong.
It's very strong, so we would say here R is equal to positive 1.0. Okay, this is the maximum value that R can take. Okay, what is R in this plot? Okay, what's the value?
2.
Okay, so R is positive.
1.0.
Is it strong relationship? Is there lots of scatter and no scatter or what?
Strong.
Very, very strong. R here is also 1.0. Okay, so the slope of the line has nothing to do with the strength. Okay, you have to ask, is there a lot of scatter? And in both of these things, there was no scatter whatsoever, right? They're all in a perfect straight line. So in both cases, R is positive 1. Okay, so both are in a perfect straight line. No scatter. So that's why R is equal to positive 1.0 plus 1.0. Okay, let's just try another one here. What's this?
Negative.
R is negative 1.0. Okay, they're supposed to be in a straight line. Okay, just imagine straight line again. Straight line, and here again another straight line. What is R here?
0.
R is 0. Okay, neither positive nor negative, straight line but flat. Okay, so R is 0. Does that make sense to everybody?
Yes.
Professor,
Yes.
can you remind me why that's neither positive nor negative?
Okay, so what does it mean to be positive? Positive relationship means large X goes with large Y and small x goes with small y. Okay? So what's going on here? Large X, if I go in the X direction, large X means I'm over here on the x-axis, right? So here's a value. Okay, and how does that compare to the small x over here? Large X and small x are associated with the same value of y. Okay, it's neither, it doesn't go for large y or small y. They're the same. So it's neither a positive direction and it's not negative, where large X goes with small y. Okay, so here the values of x and y. So over here, large X goes with the small y, right? because in terms of y, we're down here for when we're out over here. And if I go with small x, I end up with the large y, okay? So small x goes with large y, large x goes with small y. So here I've got a negative relationship. Something like that, okay? All right, let's put a little bit of scatter in here. Okay, what do you think R here is? Okay, so it's not 1 because there is a little bit of scatter. If there's absolutely no scatter, then it's 1. But here there is a little bit of scatter, but it's still a very strong relationship, right? Not a ton of scatter. So I would say R is something like 0.9. Okay, probably even 0.95. You know, as you get experience, you'll get a better idea. But it's still positive relationship, okay? So, you know, I could add some more scatter here. All right, and what do you think R here is going to be? It's probably going to be like 0.65 or 0.7, okay? And it's just as the scatter gets more and more and more, okay? You still have to ask, is there an overall positive relationship? And if the answer is yes, you know, R here is probably like 0.4, okay? I'm sorry, I'm just making these up off the top of my head based on the experience I have in looking at different plots, okay? I'm just telling you something like this will probably be around 0.4. I have no idea, really, okay?
Is the formula complicated?
It's not incredibly complicated, but it's tedious, okay? It's the, you take the z-score of x and the z-score of y and you multiply them together for every single point.
Okay.
You add them up and you divide by n minus 2, okay? So divided by the standard deviation of x and the standard deviation of y. But okay, anyway, what? No, you don't have to calculate r, okay? You don't have to calculate r, but maybe you'll see some plots and you've got to figure, you know, match the r values and things like that, okay? Okay? And again, let's just do a cloud of points here. And so something like this, probably R is 0. Okay. All right, let's do one more. Okay, can you guys see this one?
Yeah.
Yes.
All right, what do you think R is going to be here?
0.
It's not going to be 0, okay? Because what R is trying to do is trying to fit a straight line to this, okay? And so if you had to fit a straight line, it would probably look something like that, right? If you had to, this is not correct to do, but if you had to fit a straight line, it would probably look something like that. And I would say R is probably going to be like 0.5. Okay, it's going to say, hey, it looks positive. There's not a ton of scatter. There's a good amount of scatter, but it's like not crazy. And it would probably say R is 0.5. But lo and behold, what do we know? R is not appropriate to use. Okay, not appropriate. I spelled that wrong. Appropriate. Because it is nonlinear. But R doesn't know. R is just the result of a formula. So you can plug numbers into the formula and it's going to spit a number out. And so it's very important that you create a scatter plot. Because if you just go off of the summary statistics, you might not realize that you have something that is nonlinear. Okay, so let me just actually show you something. Anscombe's quartet. Here we are. Let's look here. View image. Okay, so in all of these data sets, the R value for all four is exactly the same. This is, I think it's R is positive 0.86, okay? Here R is also positive 0.86. For this one R is positive 0.86, and for this one R is positive 0.86, okay? And the only one where I would say the 0.86 is an appropriate interpretation would be this top left one here, okay? What's going on over here? Okay? Because of this 1 point, if this point didn't exist, R would be what? R would be positive 1, right? Because these points, if this point did not exist, these other points would be in a perfect straight line, and R would be positive 1. But probably somebody typed the number in wrong on their when they were entering data, and so now you have this thing that doesn't fit in with everything else, and that when you do the calculation for R, it sees this scatter, and it says R is 0.86 or something like that, okay? Again, here we have nonlinear data, but it tries to fit a straight line, and so it says R is 0.6. And what's going on over here? Here you didn't do a very good job of collecting data. You only collected when x was equal to 8, and you saw a whole bunch of different values of y when x was equal to 8. And then for some reason you decided to collect x equal to 19 or something, okay? And so it tries to fit a straight line to all the data. But really, when you only have values for x in one location, you can't really talk about a relationship between x and y, right? If I said, is there a relationship between age and height, but I only collected data for kids who are 8 years old, you're not going to be able to form a relationship, okay? You're not going to say older kids are taller and shorter kids are shorter, okay? Because we only have data for everyone of the same age. You can't create that relationship. Okay, so anyway, you have some charts in your book on page 150 and whatnot going over R here. Okay, so let's take a short break here, and we'll finish the rest of the chapter.